kind of thing. But you guys will see me Tuesday for intervention. Okay. Any other like rando questions? Anything? Okay. Let's do some connections. All right. So Gibbs free energy to do work. Generally, to get a work equal for the forward direction, it has to be a negative sign, right? Delta G would be negative for it to be available work in the forward direction. And I'm right now describing energy. So what unit would be a good unit for energy? What unit of measurement would be a good unit? I know, we talk about units and we talk about units, which is which. So what unit would be a unit of measurement would be a good unit to describe energy? Kilojoules, or just normal joules, right? So a lot of times our delta G is expressed in kilojoules per mole, but I'm thinking joules right now because we don't have a lot of reaction we're right now working with, but we will today. So I'm describing W as work, which we have described W, or work as W before. And when you talked about work, you always mentioned it in respect to the system, but we always had to consider it kind of how it interplayed with the surroundings. So if a system is doing work on its surroundings, what sign does that work have? Negative, because the system is losing the energy because it's giving it to the surroundings as it expands or so forth. If the surroundings is doing work on the system, like through compression, the sign of W is positive because we're talking about from the system's perspective. So we will play with that a little bit, but it's going to be, I think it'll be pretty well defined when we get this interplaying with batteries here. All right, so you know this. You know that with the cell potential, what's cell potential's just like variable again? When I say cell potential, you're thinking, okay, that's the unit of volts, but we're describing it as E cell. Okay, E cell is cell potential. So cell potential, if it's a galvanic cell, it has a positive cell potential. That's the difference in the potential to lose electrons between the cathode and the anode. But we know that meant a delta G that was spontaneous, thermodynamically favorable, which we're describing as a negative work, okay? Because the delta G is negative, so the work that's attained from the system's perspective is negative, because it's giving the energy away to the voltmeter as it's reading it. So we see this negative sign flip, right? Okay, and we kind of already knew that this was a true statement. Delta G negative meant a positive delta E cell. That was our basic memorization for the beginning. All right, so then after that, well, this is a little bit more. All right, so we know that that's true only for galvanic cells. We're going to get into electrolytic a little bit today, and then more so on Monday. And that's losing work, or the work is considered negative because the current's flowing out of the cell, and we're capturing it and using it for other means. So that's kind of setting up what you know, and we're going to start connecting some dots here. Voltage I mentioned earlier, and we use that unit for cell potential. But what was a volt? I mentioned this yesterday or day before. Okay, amps. Amps are coulombs per second. That's amperes. Amps were coulombs per second. What are we measuring with volts? What are you hoping to get out of a battery? Joules. You're going to get energy, right? Okay, you're hoping to get energy, so we know volt is going to be correlated to joules in some way or form. But who's delivering the energy? Who's got the energy in a battery? It's not a specific part of the anatomy. The electrons, okay? And I told you guys electrons carry around charges, okay? But the charge, we don't call it charge per se, we call it coulombs. It's the C when I say coulombs, like this. So there's a relationship between volts, joules, and coulombs, and here it is. I think I have it right here. Okay, good. So joules per coulomb is equal to a volt. And I have labeled them with some extra variables because we're going to start to use those variables to connect it to the last part here. So 1 volt is equal to 1 joule per 1 coulomb. 1 volt is equal to 1 joule per 1 coulomb. So this is saying 1 joule of energy is produced for every for the charge of the electrons coming through the battery, as we express it as the voltage differences or the potential differences between the two parts of the anatomy of the battery, the anode and the cathode. So 1 joule of energy is produced with 1 coulomb of charge as it's transferred to create 1 volt. So these are all kind of equivalencies as you consider them together. All right, so now you see Joule again, right? Well, that's going to kind of relate it back to delta G, aka the work that's done. So I'm trying to help you understand what all these equations, because this pulls together thermochem equations with general equilibrium equations with electrochemistry equations. So I'm hoping that we can make a connection here with the triangle of those three big ideas. All right, so label E cell as work divided by Q, and I'll tell you Q does not mean heat. Q means charge. In this case, there's no a heat aspect right now to electrochemistry. E cell is negative work. Sorry, there's a negative there. Negative work per Q, which is charge. So if I'm considering E cell and I take and rearrange that equation, and I take E cell, which is work, negative work divided by Q, I can pull Q up over here to the side, so then I have E cell times Q equals negative W. Got me? All right, so just rearrange. So basically now I've isolated work because work to me means Gibbs free energy. Okay, so I'm trying to get the delta G kind of out by itself. All right, so I've done delta G or pulled work out to itself. I'll get to that in a second. Now, Q, which I told you was charge, where is the charge coming from? Where's the current coming from again? Electrons, and now we actually do depend on the number of electrons that are being transferred. So Q, which is charge that the electrons are delivering, is based on two variables. How many moles of electrons are you delivering, which we'll label as N. We've labeled N as the number of moles many times. You know, in the ideal gas law, N is moles. In Kc, or politically correct, from Kp is equal to Kc to the delta N, or RT to the delta N. That was the number of moles of gas. Now we're talking about number of moles of electrons. So it is specific to the theme that this is the number of moles of electrons. And we'll multiply the number of moles of electrons by Faraday's constant. And Faraday's constant is 96,485. Many times for mathematical purposes with multiple choice questions, we'll just call it 96,500 coulombs per mole of electrons. If you ever have to do some estimations through mental math. All right, so we've taken E cell, related it to work and charge. We rearranged the E cell formula to just solve for work. Now we're thinking about what does Q really mean? Q really means charge, which is the product of the moles of electrons times the charges that those electrons carry. So how does that mathematically, or how does that work out with units? If I have Q and I say moles of electrons times 96,500 coulombs per mole of electrons, what unit is Q expressed in? Just coulombs, right? So, because that's moles of electrons canceling, leaving us with coulombs. All right, so if Q is measured in coulombs and E cell is measured in E cell, which you've been using this whole time, volts. Okay, so this is coulomb and this is volts. What is work described as, measured in? Joules. There's our relationship one more time. 1 volt is equal to 1 joule per 1 coulomb. 1 joule is equal to 1 volt times coulomb, because we rearranged the equation. But there's your relationship kind of standing out, right? Kind of making these connections, okay? And then after that, we're going to start going a little bit down. Stop here, okay. So once you see that Q is equal to N times F, which is moles times Faraday's constant, I'm plugging those in right here. So E cell times N times F equals negative work. Well, work, which we're correlating as G, those are the same thing. Do you recognize this bottom equation? Say again?
Part 3.
Yes, part 3, but delta G is equal to negative NFE. What else did delta G equal for us back with equilibrium? Okay, so delta H and delta S combination. What else? Rattling, negative RT, ln of K. All right, so if we can relate anything to delta G, we can relate it to equilibrium, electrochemistry, thermodynamics. Delta G is the connector between them all, okay? So that's kind of the meeting place. And I didn't put standards here, but I could put those little knots there to call it standard conditions. So basically it's telling you that the free energy that's available is based upon the differences in the reduction potentials, aka the E cell, times the moles of electrons that are transferred times the charges of electrons. Because electrons carry energy, or they carry charge, which we can convert to joules and determine the energy. So far, you even had a single example where you could actually calculate delta G, or mathematically calculate delta G from an electron standpoint. Everything's been theoretical. Like you have a big table of delta H's, a big table of delta S's. You can't even measure spontaneity, a disorder in a lab, right? Like, how do you measure delta S in a lab? We don't have like a scale that measures in, oh, this one's got this much disorder and this one's got this much, right? You just have to take my word for it. It's all from tables. You can't really measure enthalpy in the lab unless you get a good Q, which is from kilos MCAT divided by moles. It takes some effort, but you can get that. You can't measure delta G, because like, how do you measure something's, like, literally measure something's favorable? You can't. But now we can! What? Whoa! I can experimentally determine Gibbs. How? You just get the cell voltage, and you do the balanced chemical equation for how many moles are transferred, multiplied by a constant, done. This is the first time. Like, this should be a wow moment for you. You've never been able to calculate delta G from laboratory laboratory sense here, okay? So thank you for acting like you were wowed. Let's do a quick math units check. What's the unit for N? Moles of electrons. What's the unit for F? 96.5 coulombs per, okay, and moles, okay, and then what's E cell? Volts, okay, so moles of electrons cancel, coulombs times volts. What should coulomb volts be? Joules, stop getting shy. Those are such fun. Those are joules. Which that would be a delta G joule. If he hits you back, I'm not watching. So if you have joules here, you could easily convert that to kilojoules to do some like thermodynamic based work. Do you have like 70% of what I just said?
Yes, I'm 70%.
Okay. Moving on. Sean, are you okay?
Yeah.
I
got load.
I just explained all the mathematical relationships through logic, but this is kind of how you can connect it. So I don't think we need to write any of this down because we just did. How do you relate W, which is work, to Q? Well, Q is not really Q. Q is N times F. And then relating that to how N times F times E is equal to joules. So I think you guys are good there. You should be anyway. The only about the thing down here, no, we're good here. I think we did all this just fine. Yeah, we're good. Okay. So there, in your reading, in your NSMI reading, it talked about how we anticipate we're going to get X amount of voltage, right? We're going to anticipate that we get X amount of work. But sometimes there's things that get in the way. What would be in a battery that possibly could limit the flow of electrons? Limit the flow of electrons. What could limit? I think somebody mentioned this when we talked about a wire. Resistance, yes. So the amount of resistance that's present just inherently in metals. Some metals are more conductive than others, or different materials are more conductive than others. You could have some resistance, and it's just electrons that can't scooch along, so there's friction is what they call it. So there is a little bit of error just inherent in our calculations, because max work is not attained. So that's why I said don't write all this, because some of it is just basic understanding. The stuff in yellow, if you want to write anything, you can write some of that. But it's just basically, you're not going to always attain your maximum amount of work that you think you could, just inherent due to the resistance present in some of our wires. And then additionally, sometimes we have energy loss as heat. You guys have probably had your cell phones get really hot. Maybe battery, they're working hard, so there's some loss of flow of electrons due to heat buildup, and so that limits the amount of flow with some respect. But we always will have electrons flow because the thermodynamic nature of this reaction is we want it to flow. They will flow because we want them to flow due to the second law of thermodynamics, where we satisfy the universe to get as much disorder as possible. So flowing electrons generally creates more disorder. This is straight up out of your book. So if you guys want to read some more of that, that's for you. And then this bottom part down here, it's just saying this is our only way that we can experimentally take true measurements from the lab and directly calculate delta G. Never before have we been able to do this. Okay, this is the only place that we can experimentally determine G. Yay!
Yes.
I would move at this point, Sean.
I would move it.
Okay.
You're looking for it.
After you take a second to read, give me a thumbs up so I can move. Some of you guys are just absorbers. Okay. Okay. Let's do a calculation. Go ahead, write down or draw your cell, your galvanic cell out with this reaction. Talk to each other, and I want you guys to calculate the delta G, so the Gibbs free energy of this reaction. You will look at your reduction potential list so that I can have it as well.
So now what we're going to do is we're going to I have a question.
Yeah.
Was it flow from anode to cathode or cathode to anode?
It always
Wait,
flows.
the thing up there goes anode to AC.
Yeah.
That's what
It always flows from anode to cathode. I've drawn it so that my anodes are on the left, but it's not always the case. But the way this is described as anode.
Yeah.
Cathode. I feel like we know coppers. We dealt with it yesterday. 0.34. Thank you. How you guys? I want you guys to write out your NIE with this as well.
Oh,
Was it not? I know this one probably is obvious how many electrons are transferred, but I want you to try to continue to support your process. So what's the actual reaction here? What's the half reaction for the anode? Set it out. I'm ready. Zn to Zn2 plus 2 electrons, okay? Because we have to have oxidation occurring, so we have to show the loss of electrons. And the cathode is happening. What's happening here? Cu2 plus 2 electrons yields copper solid, because there must be reduction happening there. So you should be able to continually assign oxidation reduction based on electrons placement in the reaction and knowing how to think about charge loss. So overall, no need to balance out electrons. They're already balanced. So what's our overall reaction? Zn plus copper ion yields copper plus zinc ion. Okay, so that's our overall reaction. Alrighty. When you're doing E cell for galvanic, what's your method of subtraction here?
cathode.
So cathode minus anode, or reduction minus anode, or oxidation. This is assuming standard condition. So E cell is 0.34, thank you, minus a negative 0.76 volts. Total 1.10 volts sig figs, thank you. When you're doing subtraction for sig figs, you count decimals. You don't actually count sig figs. 2 decimals, 2 decimals, 2 decimals. Okay, so one, we know it's galvanic because it is, this is positive. That kind of gives us that double, pat on the back that we're doing good. How would you calculate delta G from this?
You're going to do the moles of electron times the constant.
So delta G equals, what's the formula? Negative Neffy. Negative Neffy. All right. So go for it. How many moles of electrons? 2. 2 are transferred. It's not 4 because 2 total are transferred across the board here. 2 moles of electrons times 96,485 coulombs per mole of electrons times 1.10 volts. All right, and you guys got it yet? I'm expecting you to be my calculators. Give me the first units first, and then we'll go from there. So I know that moles of electrons cancel. I'm videoing for these guys. I'm making sure we're very clear. So moles cancel. We're stuck with coulomb volts. So what's this number when you multiply? It's gonna be like. What is it? Louder, Alvin.
Negative 212,267.
That's everything.
Yeah, when you multiply them together, negative 212. Sorry, I heard 12 and I heard 212,000.
267.
267.
Yeah.
I hear all of you, so bear with me. Okay, that's joule. That's coulomb volts, right? Coulomb volts. So then your idea, you see coulomb volts because coulombs and volts are remaining. You have to understand that coulomb volts are actually a what? A joule. That's what I kept going over. Coulomb volts are joules. So this is negative 212,267 joules, which is how many kilojoules? Negative 212 kilojoules. Assuming many times our moles of electrons are not our limiter. Yeah. There's a negative right here. Sorry. Is that right there? Was it negative? It should be negative. It's galvanic, right? I'm hoping you guys put your negative in there. My bad if I didn't put that there. It should be negative because one is galvanic. 1 second. E cell is positive. Delta G should be negative. Those three things correlate. Question.
Okay, sig figs on this. Would you do the 1 sig fig is 2 moles, or would you do
That's
2
what I was
sig
trying to
figs?
tell you.
Okay.
This is not a measurement.
Okay.
Okay, so it's not a measurement. It's not limiting our significant figures. That's just counting number of moles. This is a constant. Many times our constants have lots of sig figs. That's truly not a measurement in itself. The only measurement we took in this lab was what?
The volts.
The volts. We measured the volts. There's 3 sig figs there. That's likely what
Okay,
we're
so
recording.
whenever you're doing up top, it's you go to 2 sig figs. Or would you? Okay.
We go to 2 decimals. Yeah, it's subtract.
And then yeah. Cool.
All right, and I'm glad we're talking sig figs because your midterm says you need it. Okay, so if I wanted to calculate the K value from this, what would I do? So equilibrium constant K.
E to the negative 1 or RT.
Not E. There's no E in that. What's the equation? Rattling. So delta G is equal to negative RT ln of K, and I could then plug in. I would plug in R value of what? 8.314 joules. I say that loud and proud. And then assuming that we're talking about that knot, so standard temperature, what's standard temperature here? 293 Kelvin, because it's going to be in Kelvin for one, and 25 degrees Celsius is standard for these problems. Oh, 298. That's an 8, not a 3. That's 2 3s together. All right. And then ln of K, what would this value over here be? If you're going to be using your units appropriately.
In the negative 2.2267.
Yeah, so the big shebang up there, so negative 2,000 or 20, this number. Or you could convert this to kilojoules and use your 212. So just make sure you're consistent there. 1 second. How would you then calculate K? After you kind of manipulate what's...
It's going to be e to the negative, it would be e to the negative g over negative RT.
So when you divide by 8.34 or 314 times 298 on both sides, ln of K equals whatever that whole mess is, right? And then, yes, E. So your opposite of ln is E.
That's what I was thinking.
Does anybody have that? Go for it, Alvin.
1.615.
Nice. Okay, so this, oops. So we have proof of concept, right? Positive E cell, negative G, galvanic, large K value, products are favored. So all those are correlating. Okay, did you have a question?
My question was, that's why I was saying earlier when I meant E, and my question was why, how come we can't just say delta G over RT equals or e to the delta G over RT plus K. Like that's all I was saying at first, and you said no, and I was confused. It worked out.
Okay.
We just
Yeah, because those aren't exactly correlated.
Yeah.
All right, let's move on to the Nernst equation now. So you guys did a little bit of work with that, but now we're talking about, this has all been at standard. What are the standard conditions for electrochemistry? Temperature, 25 Celsius, 1 atmosphere, and 1 molar. Okay, so we've assumed everything's been 1 molar so far. I think this is my next thing. Oh, this was a side note. Occasionally they'll give you FRQs that say like, I forget how this one was phrased. They give you a switch basically. So this is a closed circuit because you can have your electrons flow and then charge balance with your salt bridge. Electrons flow, salt bridge charge balances. But if you open the switch, electrons will not flow because this is like this is disconnecting the wire. So if it ever asks about like could you fix the scenario so the electrons continue to flow, just close the switch. That's it. Just close the circuit. This was a dumb question they asked, I think, in like 1990 something. But I like to make sure we're clear. That's how you do that. All right. So sometimes you don't have standard conditions. So sometimes you don't have 1 molar concentration, for example. Okay. So that's going to change up how much your driving force of your electrons are going to be pushed from anode to cathode. So you have to account for how does that influence your cell potential. You guys did this on your simulation part 2. You changed the concentrations, you saw some differences, but I talked to like 2 groups, they understood why. We're going to relate it to Le Chatelier's principle with Gibbs with K values. So quick kind of logic part first. If you have to calculate a new G, notice I did not put the not, meaning it's not standard. We will compare the Gibbs free energy to the original Gibbs free energy as it relates to the temperature and the equilibrium conditions, the initial conditions present. So the initial conditions are generally non-equilibrium. That's where we label them Q and not K. Remember that? Okay. So if I've changed up my situation where it's non-standard, I have my negative delta G and I'm adding a large positive number. What does that do to my new delta G? Makes it. Say again?
Or less.
So give me a magnitude change. Lower, higher, more negative, less negative. Tell me what I'm looking at here. Less negative. Okay, so it's negative. I'm adding a large positive number. 1, it could be less negative. Or this number could be so large it's positive. Okay, so those are really your 2 options there. But regardless, what does that do to the spontaneity? Decreases it because it's not as negative as it once was, so it's less spontaneous or less thermodynamically favorable. I like to try to make sure you know those both correlate there. So what are some reasons that you get a large positive number? Either you have a hot temperature, you heated your sample, so your T value is getting larger, or you've changed the concentrations. But I'm telling you now, the products would be what is in higher quantity than the reactant concentrations. When we're considering electrochemistry batteries, we're not talking about all the products and all the reactants. Which are the only things that matter in equilibrium? What states? The aqueous ones. If we had a gaseous one to do gaseous aerosols, we could do partial pressures. What are we not going to consider? All of our solids. The solids don't have a concentration, right? So that's why I'm saying concentration of products. I'll put ions there for you. All right, so opposite scenario, how would you have a reaction that's has more voltage, is more spontaneous? Likely, you're going to have a negative delta G. You're going to have an even more negative value. So you're going to make it a lower delta G value at the end. So if you have a lower delta G value, I don't want to say lower delta G. If you have a more negative delta G number, then what does that do to spontaneity? More spontaneous or more thermodynamically favorable. How could you do that? Drive the reaction to happen in the forward direction, more and more and more. Really, the only way you can do that is by increasing the concentration of the reactants in their ion form, of course, because what does that do in terms of Le Chatelier's? Forces a shift right. What does this do? Forces a shift left. If you aren't shifting right, you aren't making more electrons flow. You're not helping the voltage. So with this same instance, if you're limiting the production of products because you're trying to shift it left, or just limit the production of products because you have too many, you're at disequilibrium, it's going to affect your voltage by lowering it or hindering it. So those are some conditions that could possibly lead to differences in voltages. Let's do a problem with it now. Let's actually calculate. Before we calculate, here's the equation for it. So this one, plus your reference sheet. This is not on your reference sheet. I just want to verify that. Henderson-Hasselbalch is on your reference sheet. If you guys have one, look at it. Look on the back of it. Riley, I'll get you one. I just have to print another one. I tried to print on cardstock so it makes sense. So you know, find it easily. There is no electrochem Nernst equation, but what does it give you for electrochemistry? Nephi, okay, what else? They need to relate to decay. Really? Okay, it's really, below it gives you Q and T. You see that? We'll talk about that. That's what the electrolytic cells are in Monday. If we can at the end of class, we will. So there's not much given to you in electrochemistry, just the delta G relationships. This is not given to you, but you can memorize this. I found this, I use this in college. So though we don't memorize it or use it in AP chemistry now, doesn't mean you won't use it in 2 years. So I just want to make sure you know that there's this thing called the Nernst equation. But many times the questions will ask about what happens to the voltage? Does it go up or does it go down? So if you can understand the background with Le Chatelier's of how can you force it to go up in voltage or how can you limit the voltage, you will be fine. It's more of a qualitative answer than a quantitative answer. But I'm not telling you that the quantitative answers are not, our questions are not going to be on your AP exam. They certainly will be on mine. So first off, the relationships are here, the finals here. So let's start here. So this is your Gibbs free energy stuff that I just had on the board previously, talking about how can you limit the spontaneity of the reaction. But we're not really measuring G, we're measuring E. So when you measure E, I've taken delta G and I just transformed it into its alternate, right? So negative Nephi, negative Nephi. I have this being the non-standard one, which we'll be solving for. This is the standard one, assuming it's, if the conditions were normal or standard. Plugging that in, you just keep your RT on a Q. So if you divide by negative NF on both sides, what does this simplify to? Okay, it's on the board. I thought I had my shade up, but I don't. So it's right here. Okay. So negative Nephi. The cancels here, but this negative NF is also applying to the other term, so that applies over here as well. So then you'll see RT over NF right here. It canceled over here already. You with me? Okay. Now that negative applied, so that's why it's now subtracted versus added. Your L and a Q still exist. So you can either memorize this one, which I think is a little bit more taxing, because you got to remember like R, the T, the N, the F. There's a couple of constants and variables you're messing with there. But these constants, they have numbers, right? R has a number. T has a number for most of the time for a concentration difference. We're going to keep the same temperature, so that's why I'm doing just non-standard concentrations, not non-standard temperatures. N will actually be required for us to calculate based on, like we just did with our little half reactions, we looked at the moles transferred. And then F is a constant. So if you keep your R, or if you consider your R 8.1314 joules per mole K, and you have your temperature at 298 Kelvin or 25 degrees Celsius, and your F constant is Faraday's constant, you can lump those constants together, but when you lump them, they generally change it back to log, and this is just the conditions that chemists have chosen. So when you lump those, RT and the F, you can actually simplify down to this. So E cell is equal to E naught cell minus 0.0529 divided by N log of Q. And this is the one that I memorize, because it lumps all the constants together as one number. But we still need the N, we still need to find N from our actual cell to calculate the final answer. So apparently when you switch around the constants and you change your L into log, that's the number that correlates the constants. I'm not working through the math. I trust him. Okay? Just trust me on this. All right, so with that, we call it the Nernst equation. Occasionally, you'll be asked about dead batteries. The dead batteries, their electrons don't flow. Well, why? It's simply because there's no stability attained by shifting more electrons to the products or shifting them back to the reactants. It means that it's at equilibrium already. And I believe you did a little bit of reading on this already. So if you ever have an E cell that's 0, 1, it means the battery's dead. There's no voltage coming. And 2, your Q is equal to your K, which you knew that meant at equilibrium. already yourself, because that's our initial conditions of equilibrium conditions. And then as you continue to kind of see where this plays a role, it's going to play a role in this E cell, not E not cell, but E cell. E cell is the non-standard conditions, right? So if your battery's dead, it's probably because your concentrations have changed so much. One, not at 1 molar anymore. So that's why we're saying E cell is 0, not E not cell is 0. And so when you plug that E not, or when you plug E cell in to E cell up there, you hit your 0. Your E naught cell is whatever you subtract just based on the data table or the reduction potential list that you guys have. Just whatever you subtract. You plug in your constants in your N value log. You then can find the actual K value not only from delta G, like we did 2 slides ago, but from E. So this is the last equation that would allow you to get to K, assuming that you can assume as at equilibrium. That's the only time you can plug K in, because you notice I went from Q to K here. We'll work with these, but there's a number of equations that actually really connect. They're easily confused though, so that's why I want to walk through the relationships, because if you have to derive your own, you should be able to, like with half-life mechanics. Okay. All right. I want you to explain something you just learned to somebody else. Get up, talk to each other.
Let's take a walk in the park here.
I have heard nothing electrochemistry related.
That's why you can slow it out in the end and have
You learn that dead batteries don't do anything? G everywhere. We have so many letters. Don't be messing with my law of conservation of matter lab. I see you. I see you. I did tell them, guys, we're reacting acetic acid and sodium bicarbonate. They're like, what? And I was like, AKA vinegar and baking soda. They're like, oh. They don't know the names of everything yet, so I can impress them with, I'm like, yeah, guys, just copper sulfate pentohydrate. They're like, what? So it takes a little time to get that. A law of conservation, they're proving and disproving. They are supporting and not supporting the law that the law of conservation of matter exists. The balloon is to make a closed system so you can capture your gases so that you don't have matter lost, because matter shall not be lost or destroyed or created. Nope, come on. All right, so we're moving to, how can you relate this to Le Chat's? Okay, so I want you guys to do this one. It should take you 30 seconds to be able to explain this question. Le Chat's.
Then it will shift right to equal C. Yes. 13.
All right, and AJ, hold on, before you tell me your answer, you guys calculate E cell first, because we need that as a comparison. Calculate standardized E cell.
Oh, I know the answer. 1.10.
Is it the same? Yeah, it's the same example, right?
No.
Yeah, it is.
I just knew off the top of my head.
1.10 volts. Okay, I was like, I knew I'd read this one for a reason. All right, so that's our standardized conditions E cell. AJ, help me out.
So if you increase the concentration of the copper ion, equilibrium will shift to the right.
E cell becomes what?
So
More what? Make a choice and stick with it. Okay, if we shift right, what is actually happening in the battery? Mo electrons are flowing, right? So zinc is like taking those electrons, putting them through the external wire, copper's catching them on the other side. Zinc shoving electrons up, copper's catching them, so forth, right? So if we're shifting right, we're making that happen more forcefully. So if you're making more electrons flow, E cell is more positive because a stronger, and this is how you would qualitatively describe this. You can't get the phrasing wrong, okay? Just like some of the other ones have very specific ways you explain it. Because strong driving force of electrons in forward direction. Something like that, okay? So another way to describe the driving force is the EMF. What does EMF mean? Electromotive force is greater. Electromotive force is greater. Many times they'll let you do like a couple of abbreviations on the AP exam. If you want to use EMF like 5 times through some free response work, just define it at the top and keep going, because electromotive force is a long thing, right? Like IMFs they know that means intermolecular forces. But some other ones they're like, well, what could this person mean? Like, I mean, it's pretty obvious, but they have us define them up front if we need to. All right, so let's go ahead and actually before we move on, let's just do this one real fast. If zinc is increased, what's going to happen?
Opposite.
Can you describe that in words?
Shift left. E cell would be more negative because
E cell more
negative
because
strong driving force keep on us in reverse direction.
Okay, in reverse direction. How about we describe it in the forward direction, since that's the reaction that's actually happening?
Less driving force than EMF.
Okay, because less
weak.
EMF or electromotive force, or weaker, not less. Weaker electromotive force in that forward direction. We're speaking about things in the forward direction because that's the reaction that's occurring. It is equilibrium. It could reverse, but we're talking about how is it producing electrons to be read by that voltmeter.
So saying in the reverse direction, would that be incorrect? I mean, it'd be
No,
correct,
they'd probably flip it.
Okay.
I see a couple confused. Yeah, what's up, Mickey?
I thought galvanic cells can have negative.
I said more negative. I didn't say it was negative. Or I could just say lower positive value, right? We have to use our words specifically. All right, so let me, I've been doing stuff on top of my head. Let me make sure I don't have any like random things I need to tell you. Less driving force in the forward direction, less spontaneous. Yeah, we're good here. Okay. Next, calculation-based one. Right, so for that same reaction, I'll put it back up here. You're going to be calculating the voltage after 99.9% of the battery has discharged, meaning it's almost dead, guys, but I want to know the voltage before it dies. Okay? So, let's go back, write that reaction down for yourself, because you need it for this next problem.
Cn plus P2 plus.
You're trying to salvage a battery, and you want to make it last longer, you can figure it out. Some people put batteries in the fridge. That doesn't necessarily stop the reactions. All right, you should have your reaction down. You're going to take the initial as a standard condition. What am I trying to tell you? What's the initial?
1 molar.
1 molar. Okay, so if I'm saying we're starting with 1 molar, and we're figuring out the end products and reactants to then find our user concentrations and find the voltage, what are you setting up? Not an icebox, it's not equilibrium. I don't even have K value. You're setting up a BDA box before, during, and after. Go for it. What was it, zinc? So, under this condition, how much is 99.9% discharge? What does that mean? 0.999. 9, thank you. It's 1 molar, and both of, oops, sorry, not that one. That's a solid, it doesn't have a concentration. I'm hoping you guys didn't do that.
No, none of it.
So, zinc is just there, it's hanging out, it's not, it will change its mass, but we're not doing masses, we're doing ice box, BDA boxes. They can use molarity in this case, just like we can use moles. Because I don't have a volume, that's the only reason I'm using molarity. I could assume 1 liter, and I could do moles, but I think we're in good shape here. All right, so if 99.9% gets consumed because it's discharged, we're subtracting 0.999 molar over here. And on this side, yes, but what's this right here?
Zero.
Nope.
One.
You're assuming original conditions because you have two sides of the cell, right? Both of yours, yeah. This is already has molar 1 molar concentrations for the system, for the whole system. Okay. So this is one where before we have already considered the reaction is at its initial that it should be at, which is the standard conditions. Now you're right. You're taking away from reactants. You're adding to products. So you're adding 0.999 molar here. Ignore copper because it's a solid. Okay, so what's our final? 0.001 molar. This is after 99% discharge, and this is 1.99. All right, so I have now given you final concentrations. Okay, final concentrations. I want to find E cell, not E naught cell. We already know what E naught cell is. What's E naught for this battery? 1.10 volts. Okay, so we know that from doing our basic subtraction we did 2 slides ago. How would I then find new E? Say again? The Nernst equation, yes. Please employ the Nernst equation.
Because it's above 1 molar.
Because it's at non-standard conditions, yes. Which is below and above, yeah. What's the Nernst equation?
E cell
Equals
E
E naught cell
minus 0.0592 over log Q.
Now, I want you to actually put in what Q's describing, right? So we have a reaction. We know every single Q and K is just products over reactants, right? What's our product concentration? That matters. No, not the actual concentration. What's the identity?
Oh, yeah.
Zinc ion, okay? So we're putting zinc ion, the products, over copper ion. And both of these, remember with equilibrium, you use your coefficients as exponents. So those are both to the first power. I'm just making sure you know that because later I'm doing a non-1-to-1-to-1 ratio one. Okay, so that's your general setup. You're doing products and reactants. We ignore the solids. So E cell equals 1.10 volts. Oh, before you calculate, maybe you already have them, sorry. Think about it. What should happen to voltage in this scenario? Why should it go down, Binky? Don't think about what happened. Think about the new scenario. Because I know you're going to say, oh, it gets shifted right. But think about this. What's this going to do to the delivery of electrons? Right, because it's going to be so concentrated in that version, and whatever in the anode, it's going to be so concentrated, it's not going to want to let any more ions continue to form. Hence, it's going to stop losing electrons, hindering the electron flow, limiting the voltage. I'm hoping the voltage goes down. That would confirm our thought. Okay, let's make sure. So, plugging in your values, what's my moles of electrons transferred for this one? 2. It just happens to be the same exact one we just did, or very similar. So, 0.0592 over 2 moles of electrons times log of 1.99, that's zinc, right? Yeah. Molar over 0.001. Okay, and what's your guys' value? 1 what? 0.00. Okay. Sign? I mean, not sign. Unit? Volts, okay. Did it go down? Score, yes it did, okay. And so this right here, this moles of electrons is actually not a part of our overall. Logs, your molars will cancel, and then that's our volt, so it did go down. At that new condition, it would continue to shift left to hinder electron flow. Can I go forward? I have another 2 that we're going to do. Okay. Do I need this right now? I don't need this right now. I already did something with this. All right, so I'll come right back here. Go to, dang it, where's that questionnaire? I'll come back to the concentration cells. I want to do this last. I want to do this last question here. Go ahead. You guys started. Similar process. And you always consider initial being what initial concentration should be. Chem gases.
Hmm? Yeah.
What's the E cell? Yeah, what's up? Oh, I'm gonna have to give you one. There's about a million charts like this. There's no FE3, FE0. I have it right here. In the back of your book, you guys have like everything. I have it in my notes. Hold on, I just have to figure out what it was. Okay, here it is. So E cell, which is E of the cathode minus E of the anode. Who's at the cathode in this example? Think about the charge change. Iron, so cathode is going to be reduced. So we're talking about iron 3 going to, iron 3 plus 3 electrons going to iron solid. That reduction potential is 0.33 volts. That would be given to you on your sheet. That particular one doesn't have it on there. So that's 0.33 volts. The anode, which is zinc to zinc 2 plus, is negative 0.76 volts, because I think we just used that one before.
Yes.
So you guys should be able to find E cell now.
1.09 because that was on 1.34.
1.09. True story.
This is where I have a question.
I'm gonna see if you guys.
Of electron transfer is 3 over 2. 3 over 2. That's not right.
1.5 electrons? No, I'm just saying it a little bit so I know you guys are probably doing. So Courtney just said, don't you have to balance the equation? The answer is yes. When you balance the equation, you're going to have probably a different number of electrons than what you thought, because you can't have one half reaction deliver 3 and the other one take 2, or vice versa. Yes, you need to balance it first. That's why I said consider stoic relationships here. You got to get some more ratios. That's also important when you subtract for the D part of BDA. You have a question like this on your test for me next week, so I'll make sure we're doing this one.
Yeah, because the FE put over 1 put over 0.04 minus 1.
What? Say again? Oh, yeah. You good? Before you get too far, can somebody tell me how you would set up your Q expression here, or your K
It's going to
expression?
be the concentration of FE to the third is,
Okay, so let me plug my numbers
or
in here.
Z, I'm sorry, Z into third.
Z, what was it? 3, 2, 2. So when you plug in, you get zinc 2 plus to the third over.
FE 3 plus to the second.
Yes. That's why I really want to point out the stoic relationship here, because this is our equilibrium constants again, where you're doing products or reactants, but you're still using coefficients as exponents. Okay, now, does anybody want to now that you have your general setup, you know you had a balance, you know you had to get your total moles of electrons to be 6. You know your general setup over here is going to be after the reactions over, you're plugging those values in. Let's talk about this stuff now, okay? So we don't need any of this. But what's the other information we know?
0.005 is after.
0.005 is after. So how did we get from here to here?
Minus 0.995.
All right, so you guys are saying total subtracted 0.995 molar. But the relationship is important.
Oh.
So you divide that by 2 to figure out kind of what X is, or the portion, the moles related. So what is that? You can do it. You can do it in a couple ways actually. But so when you divide that by 2, you're actually subtracting like 2x here, but that 2x equals this. So x is equal to what? 0.49. That might help if you're thinking about relationships. I'll do it another way in a second too if you're more comfortable with another way. So technically, you're subtracting a significant portion from this, but it's actually 2 parts because of the relationship of 2, and over here we'll do 3. So if you subtract 2 portions here, you're adding 3 portions here, but that's 3 times this. So you're adding what total? 1.4925. I didn't write that down, so thank you. Okay, so total, after all that mess is subtracted, you got 0.005. What are you at? What's the total over here? 2.4925. Now that you see the relationships, the ratios come into play, now you can plug your data in here. So I want you to process that a little bit first before I started solving. So now you plug E cell is equal to E naught, which was what, 1.09? Is that right? And 0.0592 over 6 moles of electrons, because the net was 3 times 2. Log of 24925 to the third divided by 0.052 to the second. A lot of stuff to plug in your calculator, really easy to make a mistake. Okay, do it in chunks. Anybody got an answer for me? 1.03. Oh, and I didn't even ask you guys to predict. Dang it. Okay, so this is 1.03. Can somebody explain qualitatively why that made sense? Initial concentrations? Fine, I'll go for it, Courtney.
Because the concentration is linked going up in the end, so it has to shift back. I just forgot. And like, so the voltage is less because the reverse.
The reverse
reaction is less. The reverse reaction's favor is oh, I don't know how to say it, but I can't.
You basically have it. So you're
the driving force of the forward reaction is weaker.
Thank you. The driving force is lower, the driving force is weaker, hence the voltage drops. It was 1.09, now it's 1.03. Give me a thumbs up if you could do that on your own. Now you've seen your mistakes.
I can't.
Without coefficients, I'm sorry.
No, I forgot.
Oh, you forgot coefficients, okay. So, but as long as you have your one big example down, I think you guys will be able to reflect on that. But I always set up this first, and it helps me realize that I have some coefficients maybe I deal with, and then I go back and kind of use those coefficients as ratios. All right, and you know what? Let me take a break because I know that I've been here for a while. Go ahead and pull the packet out. I'll have you guys start on all these. The last thing I'll do is a concentration cell, which is just a particular galvanic cell that has the exact same name as cathode, so you don't have a voltage difference that you do that. So go to, it says page 5, practice problems using your cells. I have assigned 1 through 5. Work with me, guys. Let me pass it out. I was on 1 through 5. You should be able to do 1 right now, 3, and 5. The other 2 are concentration cells, so you just can't do that quite well. So just start with 1, so you guys get a break from me. We have about 30 minutes left in class. There was 1 and 3. Sorry for the lecture heavy day. I think we have like 2 of those, 3 of those this unit. Start with 1 and 3. About Le Chatelier's a lot at first. Think about how things would cause disequilibrium and how we can shift. So what everything's got on it. I'm going to give you some tips. You absolutely should write out the full-out reaction for this, because you're thinking, oh yeah, I know what's in anode, and I know what's in cathode, but you're not thinking about the reaction. Write out the reaction for this, because I just agreed with you, what you were saying, but you didn't think about the reaction. So write the reaction out, and then you'll think about how does it shift, because don't think about shifting left and right as like the compartments, right? You care about what's in the compartment. Think about what the reactants are and the products are. The compartments left and right versus products left and right are different. You guys can totally do 2. I don't know why I'm skipped around saying it. Can we go over number 1? I was hoping you guys would be in a place where you could get through number 1 by yourselves. So if you've written out your reaction, what's your reaction for number 1 up here? 3 silvers plus 3 silver ions plus aluminum yield. Okay, great. So, okay. Whenever you're drawing this out, you write your reaction, you think about your anode and cathode. You should be able to determine your anode and cathode from the basic reaction here. But I'm a drawer, and I like to make sure I'm thinking about what's actually happening. So, who is in the anode? Aluminum and aluminum ion, right? Before this whole process is even occurring, that's an aluminum ion concentration of 1 molar. Voltmeter, and then silver, and a silver concentration, or silver solution in 1 molar. Okay, so eventually this battery will get to equilibrium, which voltage will be 0. But it's still in flux, right? It's still going to be sending electrons from the anode to the cathode, and your salt bridge is doing the balancing of ions work. So there is an equilibrium here because the ions that are flowing in the salt bridge are helping to achieve charge balance so they can continue to do their half reaction, they can do their half reaction. All right, so whenever you add water to these aluminum, was it aluminum, what did it say? To the anode, thank you, okay. So when you add water here, what is it doing that is meaningful? It is what? Of aluminum, right? So it's decreasing aluminum ions concentration because it's diluted. So despite the fact you diluted this, don't think about this with left-right stuff. Think about this reaction. You basically diluted and decreased the concentration of the aluminum ion. What does that cause to equilibrium? Okay, so that disequilibrium, we're going to shift right. Yeah. You've not drawn it galvanically. It doesn't say it's powered by an external source, so you have to consider it's not going to go unless it's galvanic. That's the importance of knowing, looking back at your reduction potential list and stating who's going to be the one oxidized, who's going to be the one that's reduced.
So the one that's higher.
The one that's higher, meaning more positive E, is the one that's reduced. Higher positive value and reduction potential means you have a high potential to be reduced. That's why it's called reduction potential. All right, so if this is lowering, you're going to have to shift right to make your ions increase. So what's going to happen to the electromotive force? It's going to make it stronger. If you're shifting right and you're going forward, man, this aluminum's like, take my electrons and make me an ion. You're going to force the electrons to flow. EMF will go up. So adding water to the anode dilutes the aluminum 3 concentration, which causes a shift right in the Bev equation. Due to the decrease in the concentration of product, it will increase E cell because it favors a forward reaction and increases the driving force of the electrons. All that kind of goes together. Cool? How about decrease or changing the size of the aluminum electrode? Change the size, anybody? Nothing. Are solids involved in equilibrium? No. Okay? Doesn't matter if you change the size or the mass of that object. It is not controlling the equilibrium. It's the surface area, it's the concentration, it's the temperature. The solids are not included in equilibrium, so if you change a solid, it cannot even disrupt equilibrium. Now, if you totally removed it, we'd have a problem, but that's like the extreme. If you take silver nitrate, you add some silver ion, but it's not going to change the concentration, what's going to happen to equilibrium? Nothing. No change. No change to concentration. No change. No change to EMF. Okay? If you're not changing concentrations, you're not going to change the electromotive force because there is no additional stress on the driving force. Adding hydrochloric acid will do what? Over here, or in the silver. It'll what? Increase concentration of what? I'm adding hydrochloric acid. Hydrochloric acid, how will that impact this concentration? Because it's not, oh, so good point. Yes, I will increase concentration of ions there, but those ions don't mean crap to this reaction. It's this equilibrium reaction that we are concerned about. There's no chlorine and there's no H+. That is a true statement though. But what will this HCl do with silver, guys? Make what? Silver chloride. And what is silver chloride? A precipitate. So hence, what are we doing to silver's concentration? Lowering it. Okay, so we're lowering the concentration of silver by precipitating it. Chlorine's hanging out, but who cares? It's not in our equilibrium. So what does that do to our overall reaction? It's going to shift left because we are decreasing the concentration of a reactant to re-achieve equilibrium or re-establish equilibrium. We're going to shift to make more of that silver ion. Hence, what happens to electromotive force? Decreases. If you shift left, you're not allowing the electrons to flow from who? Who's the anode? Aluminum, yeah, because if you're forcing reactions in the reverse direction, aluminum's not going to release electrons. If anything, it's going to try to reverse it, but it's very difficult to reverse a reaction in a galvanic, so that's why I just say hinders the flow of electrons. So shift left lowers the electromotive force. Okay, and number 2, I might save the rest of this other stuff for later. Number 2, have you guys gotten that far? Started it. Go ahead and keep working. I'll let you guys go through 2 and 3. if I have to, I'll do number 4 with you guys later, because I'll just wait and do the concentration cells. Keep working. I want to make sure you're pretty clear before you go on some of these little details. Yes, the answer's on the bottom of the paper. When I made this answer key probably 5 years ago, I had a different reduction potentialist than what's in your hands now, so if it's a hair off, it's because I had to do this. It always change constantly. Okay, so I'm gonna pause the video now. On these number like 2 and so forth, I want you to think about like, is it gonna shift left? Is it gonna shift right? What should happen to voltage? Before you do it, put your little hypothesis at the beginning so that you can verify it. So what you should have seen on number 2, we got the 0.51, which we just discussed. The bottom answers might be a hair different because of my previous reduction potential list. Whenever you saw this increase in nickel and then a decrease in zinc, increasing in nickel, decreasing in zinc, certainly should have shifted which way?
Left.
Increase in nickel 2 ion would mean I have more reactants that would stress that, and a decrease in product would mean that would be a stress. So both of those agree to shift right. So what should happen to EMF? It should go up, right? So it did 0.55 versus 0.51. You guys okay with that? All right, so goals. Finish up as much as you can on the Nernst 1 through 5. There's that number 4, which is a concentration cell we haven't learned how to do yet, so skip that one. 2 FRQs, 88 and 83. Turn like maybe 2 or 3 pages in your packet, you'll see those. Circle 88 and 83. And then I'm going to play the announcements.